Hello, everyone. Michael here. Where We Go Next will be back with a new episode in a week. Until then, I wanted to share another one of my favorite episodes with you. This one is from 2023, and it's with Andy Lapsa, the co-founder of Stoke Space, which is aiming to make fully reusable rockets. To put that in perspective, as of now, the world's most successful rocket company, SpaceX, uses only partially reusable rockets. Each rocket has two stages. The first stage booster, which lands back on Earth and is reused, and the second stage, which contains the payload that is delivered to space, like a satellite. The second stage currently burns up in the atmosphere, but Stoke Space plans to have its first and second stages land safely back on Earth. When you listen to Andy talk about what he and his team are doing, you can't help but feel excited about the future they want to build. I hope you enjoy our conversation as much as I did, and I'll see you next week. I'm your host, Michael Callahan, and wherever you might be now, this is Where We Go Next. Andy Lapsa is the co-founder of Stoke Space, a reusable rocket company started in 2019 with the knowledge that fully and rapidly reusable rockets represent the inevitable and necessary future of the space industry. Prior to founding Stoke, Andy was one of the original three members of Blue Origin's BE4 team, where he held architecture, design, analysis, and development test leadership roles. Andy, thanks so much for joining us.
Thank you so much for having me.
Now, I come from a storytelling background that informs how I see the world. And every great story, whether it's a book or a television show or a movie, begins with what is known traditionally as the inciting incident. It's the event that kickstarts the plot of the movie and gives the story its momentum, its drive. So if we're to truly understand the story of Stoke Space, I think we have to start at the beginning. You were with Blue Origin for 11 years, from 2009 to 2019, either as a propulsion engineer or a director overseeing rocket engine development. Founding a company is difficult, precarious, I think often thankless work. So why did you and Tom Feldman, who's also formerly of Blue Origin, decide to co-found your own rocket company rather than continue work at an already established and funded one like Blue Origin or a competitor like Rocket Lab?
Well, I think you nailed it in that it is not the easy path, but I think it's I think it's the right path. I think, look, if you look at our industry and really try to abstract yourself and look at our place in the world and our place in history, it is a really magical moment that we're in right now. It is the first time where you have the kind of the nexus of the three ingredients that are needed to make a really huge change in the world. And those three things are, first of all, there's commercial incentive, right? There's commercial applications that finally make sense to be doing in space. And that's really never been true before. So we'll obviously get into those, but that commercial incentive is there. The second thing is we have the technical know-how. We've been launching rockets since the 1960s, but in a lot of ways that was, or I guess, technically the 1950s, but in a lot of ways that was ahead of its time, right? It took massive government efforts, literally hundreds of thousands of people to pull these things off. And now the technology has caught up where we can do that type of activity, but with much smaller teams and much faster. So that's there. And then the third thing, which makes now a very unique time, even compared to 10 or 15 years ago, is that you have the workforce, the skill sets in the workforce that have gone from a completely blank page all the way through development and flight. And you have individuals who have seen every single point in that process. And I think to some extent, you had that a little bit in the 1960s where things were being tried and tested, iterated, and flown. But again, like I said, there were many tens and hundreds of thousands of people on these programs. So it was hard for one individual to see that end-to-end process. Today, it's being done with much smaller teams in a very similar time frame. And so it's the first time in history where you have these very unique skill sets. And so you have those three really, really important ingredients all coming together, and you have a chance to do something really special. And maybe I'll add a fourth one in the political environment where development of space, much like any new expansion, has pretty huge, political implications. And you need a set of rules, and you need the ability to enforce those rules as you go out and expand into this new area. And so there's defense and national security implications that are really starting to heat up in space. And all of those three things are coming together right now to make our development of space very important.
I think those details about the why now and why at this moment in time that these rocket companies are all beginning to kind of sprout up, if you will, in the private industry are all happening right now. I think that those details really help ground the audience in understanding why now. But I'm not sure that those details help us understand why Stoke, right? As opposed to why you wouldn't go work for another company rather than found your own.
Well, this is great. It was not intuitive to me, in perfect honesty. It was not intuitive to me to start my own company.
Understandable.
Especially one like this, right? It is hard. It's, obviously capitally intensive. We have to do things that I've never done before. And, that's thrilling, but it's hard and it's not intuitive. So why did we start Stoke? We started Stoke because, first of all, you have all those ingredients coming together. In my personal journey, I was looking for what was next. I very methodically went through the companies in our industry. I thought long and hard about what the inevitable state of this industry looks like. I thought about what the game-changing technologies need to look like. I thought about we are building a huge, massive, in fact, multiple huge and massive industries in space. And so if we're going to go build those things, I think that we had better do that in a way that's sustainable and scalable. So what does that look like? And the bottom line is I go through and I found myself looking for really three things in the next company that I was going to work for. I was looking for the right thesis. I was looking for the right team. And I was looking for, however young the team was, I was looking for a demonstrated pattern of habitual execution. And long story short is I couldn't find those three ingredients in another company that was out there. And, along this journey, I was talking to Tom as well. And I think both of us realized that the company that we think needs to exist doesn't exist. And so here we are.
For a lot of our listeners, they'll hear those qualities that you were looking for in a company before you and Tom started Stoke. And the first company that might jump to the layperson's mind, it certainly did for me when I was doing research on Stoke Space, was SpaceX. We're about to dig into the ambitious nature of your company's mission and rocket design in just a second. And I know that SpaceX was another company that you were considering before starting Stoke. About Elon Musk's company, you've said, quote, "They unquestionably have an amazing history of execution, of awe-inspiring stuff that has absolutely transformed our industry. But I do think there's room for a different style of company." We talk a lot with people who come out of SpaceX after 3, 5, 10, or 15 years, and they're shells of their old selves. They're burned out, end quote. And I think this is an eminently sensible perspective for me. You and Tom are both fathers. Life is short. But I was hoping as we're starting our conversation, you can kind of help me square that circle, right? Like I work in the video game industry, which over the last few years has kind of become almost infamous for burnout. You have developers working like 120, 140-hour weeks to try and make these impossible deadlines to release these video games. And these are video games. This isn't rockets that might take people to space one day, which is a life and death matter. So I guess my question is, everything I've read says that SpaceX employees work anywhere from 80 to 120 hours a week. Is it possible, in your view, to be an ambitious, innovative company and have a healthy work-life balance? Can you do awe-inspiring, transformative innovation working 40 to 60-hour weeks?
This is the grand experiment of Stoke. Let me respond to your question in two ways. The first thing is the place in the marketplace, I think, is number one important to talk about. Let me go back to the quote that you read out. I do have the highest level of respect for everything that SpaceX has done. It has inspired our industry, and it is almost solely responsible for the existence of the commercial space economy and everything that's to come. So we all obviously hold a huge amount of respect for everything they do. In the marketplace, I do think that there's a place for an alternative to SpaceX. SpaceX is building really amazing things at the grandest scale possible. And that's important for certain parts of the market, right? It's important to build massive infrastructure in space. It's important to perhaps go and colonize Mars, but it's not necessarily what all of the commercial customers are looking for, which is a way to get to a specific place in space, a specific orbit at a specific time, right? To draw an analogy to the airline industry, you and I can go just about anywhere in the world that we want at any time to any place for a frankly ridiculously low cost of about $5 per kilogram. And In SpaceX's case, they are massive vehicles. They are aggregating a lot of satellites all into one mission. So that process is complicated and time consuming. They go on their schedule to their location, and it may or may not meet what you're looking for. And so my whole point here is that while it has been game changing, there is room for a different service that is complementary. And frankly, they both help each other advance each other's cause. So I think the market is hungry for an alternative. That doesn't mean that SpaceX is bad or different or whatever, but there's a place in the terrestrial marketplace for airplanes and trains and 18-wheelers and sprinter vans and cargo ships, right? And the same is true for space. So the whole point is that there's room and a need for multiple companies and multiple services. So that's part one. Part two is, this is the question that I've asked myself many times, and I ask of our company. Can you build a company? Can you build a culture that executes as fast as SpaceX without burning people out while maintaining a healthy relationship with friends and family? That, like I said, is the grand experiment. Frankly, I don't know. I think that our demonstrated record of execution right now is excellent. I think we've been able to maintain some level of that balance. But you referenced 40 to 60 hour work weeks. Look, maybe sometimes they're 100-hour work weeks. And we have deadlines. We take them seriously. It is hard. Things don't always go right. We have to respond. And so to me, key is to figure out, how do we make that work for everybody? And I don't know the full answer to that question, but what I do know is that we can work from a place of empathy, from understanding. I think that one pillar of making that work is creating flexibility for everybody in our company. So that's the ability to work on site or remote. That's understanding childcare challenges, right? Kids get sick, school gets canceled. I know that there's been multiple times when, whether it's a federal holiday or a day where school is closed for either teacher conferences or teacher meetings, that I didn't see coming, and I have to figure out what to do. So flexibility is important. And we try to build that into our workplace and our work culture, in a way that maybe doesn't exist elsewhere. Sometimes we do have to respond and work really long. What I would say is, when people are what's called critical path, when they are responsible for the thing that is, I guess, holding up our next milestone, they're going to work really hard. But we understand that this is a team effort, and that person's going to bust their butt to get their part done and then hand it off to the next person, right? So it's like a relay race. That person might be surging and working really hard, but they can pass the baton to the next person then. And in between, there's a valley where they can have recovery, catch up on other elements of life, et cetera, right? We try our best to kind of plan those things out so people can plan accordingly.
Yeah, that makes sense. It seems like you're pursuing kind of like a work-life balance that almost would kind of look like a slinky, right? Something that contracts and expands depending on the needs of the mission of Stoke at any given moment, rather than a company that forces its workers to work, 100-hour weeks every single week, no matter what, because that's just part of the company culture.
Yeah. And I've heard from people, whether it's SpaceX or other companies, where, that's the expected requirement, and you just feel like you have to be there 80 or 100 hours a week or whatever it is. And I can guarantee you that those people are not working at maximum efficiency.
Yeah.
It's extremely draining. If you look at brain activity, brain research, sleep and exercise are two of the most important pillars for your brain to function at a high level. And when you're working 80 and 100 hours a week, that's not going to happen. Maybe you can surge to that level for a short period of time, but it's just not going to happen, right? You can't get into deep thought. You can't get into what's called flow when your brain's in that state, right? So you've got to be able to create the balance. I think that's important. I think that you can work more efficiently with let's say 10 years of experience or something. You kind of know a lot of the potholes to dodge, and you can work more efficiently that way. But that also typically means that you've got other portions of your life that are important. And so, yeah, try to create efficiency in the workplace that way.
You said a couple things in your answer that I think helped transition us to the next phase of our conversation. You mentioned that it's a crowded market, and indeed it is. There's dozens of launch vehicle manufacturers in various stages of development or production right now. And then you also mentioned, why airlines are so cheap, why it's so cheap to fly from one part of the world to the other. And I think the big key to that is that after you use an airplane for the first time, you don't have to dump it into the ocean, right? The fact that airlines are cheap is because you get to use the airplane hundreds, if not thousands of times. In an interview from 2021, you said, quote, "We're still in reusability 1.0, and it's time to go to reusability 2.0, end quote. So why and how are Stoke's rockets truly reusable when its competitors aren't?
This is a great question. The first thing I will say is that the reusability is part of the reason why airlines are so cheap. The other part of the reason is because they turn around, in a lot of cases under an hour. I think Southwest is the one that's famous for, kind of coining the phrase that an airplane on the ground is not making money for you. And so you can have a fully reusable airplane, but if it only flies 12 or 15 times a year, guess what? It's not that cost efficient. And so it's not only the reusability that's important, but it's also the ability for that capital asset to fly and create as many revenue generating events as it possibly can per year. And so that is a lot of what I mean by reusability 1.0 versus reusability 2.0. Today, where we at in reusability 1.0 world is we've kind of proven to ourselves that we can do this, right? And that is a necessary first step. But the obvious next step is to take that knowledge and then turn it into a system that is operationally reusable, something that can come and go from space and turn around in what today is a ridiculously short timeline. And I think that a 24-hour turnaround is more than achievable. But that system is a different system than a reusability 1.0 system. It has to be developed and designed from the get-go, kind of architected from the get-go for that level of operability. So there's a lot of things that you have to think about differently in order to operate a vehicle in that context. The other thing that I will say is reusability 1.0, what we've demonstrated so far, we've demonstrated that the first stage of the rocket is reusable. So typically, rockets have two stages. The first stage is the big one that you see leaving the launch pad, and the second stage is smaller and is stacked on top. And then up out of the atmosphere, the first stage drops away once the propellant tanks are empty. Once the propellant tanks are empty, this thing is just excess weight that's getting dragged along. And so the strategy is to drop that away, and then you ignite the second stage. And the second stage is the thing that actually goes to space and deploys the satellite. Right now, second stages are all thrown away. The rocket engine is thrown away, the tanks are thrown away, the avionics and harnesses and everything else that is a significant cost gets thrown away. Not only is it thrown away, but it burns up in the atmosphere. Sometimes that's controlled, sometimes that's not controlled. Sometimes pieces of the debris, even though the stage burns up, pieces of the debris make it all the way to the ground. There's a number of examples where you have debris from second stages that are scattered around. And as you start launching hundreds and thousands and tens of thousands of times a year, that's obviously not going to cut it. And so that's the piece that hasn't been solved yet by our industry. We've got to figure out how to make reusable second stages. And we've got to figure out how to make these things turned around very quickly. So that's what I mean by reusability 2.0. We've kind of proven to ourselves that the physics of reusability work, the economics of reusability work. We've got to take that next step, though.
The reusability of Stoke's second stage seems to have two main components that most competitors haven't seemed to solve for yet: heat shield design and second stage engine design. So I'd love to start with the heat shield. The now retired space shuttle used silica tiles, which were great at insulation, but extremely fragile and prone to breaking, which eventually led to the Columbia disaster in 2003. SpaceX's upcoming Starship, which will also have a reusable second stage, is protected by, I believe it's hexagonal ceramic tiles. In a recent podcast appearance, you said, quote, "I know SpaceX has done a lot of material science on their tiles. I would be shocked if they accept anything that's as fragile as what was used on the shuttle. But when we were starting, that's a science project that I don't know how to solve. We wanted to make an executable engineering program that's bulletproof. Even if the tiles are tougher and not as brittle, they, being SpaceX, still have 20,000 tiles that all have to be perfectly attached. If one pops off, then it's probably looking like game over," end quote. Stoke Space is pursuing, I believe, a regeneratively cooled metallic heat shield. So why is this the best path forward for Stoke, and why is it a bulletproof one?
First of all, thank you for your upfront research. This is great. Like I said, the vehicle in reusability 2.0 world has to turn around very quickly, right? Within 24 hours. And in that context, you have to think very hard about two things. The first thing is, what are the things I have to do in order to get that vehicle ready to fly again? And the second thing is, what are all the things that I cannot possibly do in that 24 hours? In other words, what do I have to cut out from the concept of operations, the operations flow? what I know you cannot do between flights is do detailed inspections of the heat shield or the vehicle, right? You cannot deploy armies of technicians to inspect and refurbish these tiles. The shuttle, for example, I believe had used 30,000 person hours between flights just for attention on the thermal protection system, right? 30,000 hours between flights. That's not going to work in a 24-hour turnaround environment, right? So from a design perspective, what does that mean? That means that I have to come up with a system, or we have to come up with a system as an industry that doesn't need to be inspected. And if it doesn't need to be inspected, then it has to be a system that's so robust that even if there are flaws in that system, it's going to work just fine, right? A lot of people don't realize that airplanes fly all the time. They fly with flaws in them. There are levels of redundancy in there, but there are also things designed for passive failure modes, and there are things that are designed to withstand some level of imperfection, right? There are cracks in the structure of airplanes and the wings that are there while we fly on them, but there are very tight protocols on scheduled maintenance, inspections, and things at certain times where those flaws have a certain size that are allowed, et cetera. Okay, so why is this important? The system that we've built, the metallic heat shield, is important because it's ductile, right? Any piece of sheet metal you can take and you can take a baseball bat to, you can bang it, you can bend it or whatnot, and it's not going to shatter, right? So it's ductile. And that means it's robust to things like ice strikes, which is the thing that took down Columbia. It's robust to bird strikes, which we hear about in aircraft world all the time. It's robust to things like, mundane things like mechanics dropping wrenches, or, there's pictures of people on man lifts trying to work on heat shield tiles and things like that, right? So all of those things are imperfect. And in a world where this vehicle is flying hundreds and thousands of times, those things are going to happen on the heat shield. And it's got to be able to withstand those things. Not only does it have to be able to withstand them, we have to be confident that it's going to keep working even in the face of those things. So that's the system that we've designed. We've designed it to be made out of everyday sheet metal. It's robust, it's ductile, has what we call passive failure modes. If there is an instance where small cracks start to form in the surface, because it's actively and regeneratively cooled, those flaws are overcooled in our case. So it's what we call a passive failure mode. Whereas if you have a crack or a flaw in the tiles, now you have screaming hot plasma that's slicing through this crack and leads to a catastrophic failure mode. And so there's a lot of good things about this approach that I think feed directly in that ability to turn around the vehicle quickly.
Some of the best products are made by having all of their design choices funneled through like a single goal. I think with Steve Jobs, for instance, with the iPod from the early 2000s, every design choice was funneled through the goal of user simplicity, right? There was this famous story of he wanted to be able to get from the home screen of the iPod to playing a song in 3 clicks or less. And his developers kept saying, like, there's no way we can do that. We have to go through too many folders. He's like, I don't care. You've got to get us there in 3 clicks, because user simplicity in the UI and the overall experience was the single funnel through which everything was put. And it sounds like so many of the design choices at Stoke Space are being funneled through the single core goal of being able to turn around a rocket to launch again in 24 hours, which is really cool. The other thing that kind of sprang to mind when I was listening to you, Andy, is like when you were describing why you're not pursuing tiles and why you're pursuing the metallic design, when the answer seems this obvious, right? And knowing that other rocket companies are staffed with, hundreds of brilliant engineers, I'm sure all of these companies, the question that starts to burn inside of my head is, why hasn't everyone else pursued the path you're taking?
Well, let me respond to both of those things. First of all, I completely agree with you with respect to the focus, right? That, in essence, is why we concluded we had to start this company. There wasn't another company out there with a singular focus of designing through that reusability 2.0 lens, right? Like I said, it has to be something that's architected from the beginning in these vehicles. You can't back into it later and find yourself on the reusability 2.0 curve. Just, it doesn't work that way, right? And you've summed it up. That's why we had to start our company, because it didn't exist yet. To SpaceX's credit and Elon and Starlink's credit, that's a reason why Starlink is very successful. You have people who take their Starlink out of a box and push the on button, And then internet comes, right? It's a massively complex problem. And I know that there was the same thing you just said. The engineers are like, well, you can't do that, right? Like all of these things have to happen. And Elon pushed back and said, no, take it out of the box, push on, there's internet. And they figured out how to do that pretty well. And I think that's what makes a successful product. You have to have that singular focus. And for us, that's the 24-hour turnaround. Reusability. Okay, what was the second part of the question?
When your non-tile design seems as obvious as it does when I'm listening to it, why didn't all these other brilliant engineers pursue it?
Well, like I said, I think it's a surprising result, and it was a non-intuitive result for us to realize that it wasn't being worked on with the focus that I think it needs to be. But I would also relate to you that this entire industry is ridiculously young, right? It is not even the first inning, in my opinion, in the space industry. So if you even go back 5 years, the commercial space sector was effectively non-existent. I think the ingredients were in place and people started to realize that there needs to be an alternative to what SpaceX is offering. There's a strong need for a much more responsive direct to final orbit service. And so you had people kind of racing to get to that market. And in my opinion, the miscalculation was that, yeah, there's a strong need for that type of complementary service. But at the end of the day, it's got to be affordable. And it's hard to deliver that service using a disposable rocket. Impossible to deliver that service in a price competitive way with a disposable rocket. And so I think there was this race to the market. People were focused on simply getting to the launch pad and weren't focused on really the end state of the industry and starting to work on that path from the get-go.
Speaking of singular funnels, right, that kind of dictate design choices, isn't one of the reasons why tiles are often used is because a lot of decisions around rocket engineering are all put through the funnel of weight, right? Like every bit of weight in the rocket itself is weight that can't be put into the payload that is eventually carried to space. So does your heat shield affect the rocket's capabilities at all, either the final payload weight or its ability to send a satellite into the much higher geosynchronous orbit that is traditionally used by Earth monitoring satellites?
Well, the answer is yes. If you are building a disposable second stage, then there are 0 pounds on that stage that are, let's say, unnecessary. Every single pound contributes to getting to orbit. And the moment you decide to try to reuse it, you are adding systems, you are adding mass in order to get that vehicle from space back to Earth. You are reserving some propellant even, right? Extra propellant mass to do a deorbit burn and whatever steering and recovery and landing system that you have on there. That's all added mass. And on the second stage, every single pound of mass that you add is directly 1-for-1 a pound of payload that you're no longer putting up. So that's the question for the whole industry is, can you do that in a way that's mass efficient? And for us, the question was, okay, we like this method of cooling that we're using. We know that it's robust from our background building engines. In fact, we use the strategy to cool rocket engines in an environment that's actually 10 times worse than the reentry thermal environment for the vehicle. So we know it works. The question is, can you do it in a way that's mass efficient? And the way that we've solved this problem is by building those efficiencies into the system in a couple of different ways. The first way is with our propellant selection. We're using liquid hydrogen as the fuel instead of a hydrocarbon or other propellant type. And what that does is give us, by a lot, a much higher, let's call it gas mileage, right? It's a higher efficiency that we use on the second stage, and that gives us the extra elbow room we need to add these reusability systems. And that actually translates into a number of pieces in the mission where we actually have better access to the higher energy orbits like geosynchronous orbit, or there's some other ones that are interesting to different customers further out. The further in space we go, the more this architecture pays off because the gas mileage effectively is much better on our system. So that's part one. Part two is it's a non-trivial problem, obviously. That's why it hasn't really been solved yet by the industry. But what we've done is come up with a system that is, I guess, highly integrated, and we get our efficiency not maybe from the component mass, but from the system level solution. And so even though the heat shield may be extra mass, we find those efficiencies in other places. Those things include, for example, like the way the load of the thrust of the vehicle is carried to other parts of the vehicle. That's a system level efficiency. We've done this without really adding separate systems, for the reusability. We use the same system that we use during the ascent burn, the way up. We use the same system for the way down. That was the crux of the problem. And that's what my co-founder and I spent a long time thinking about in the initial architecture of the vehicle. You just kind of go end to end, and at an individual component level, maybe you could argue that things are heavier, but at a system level, it is quite efficient. Quite frankly, like if we didn't come up with something that we thought was really a go-do, an engineering challenge and not a science challenge, then we wouldn't have gone forward. We wouldn't have looked for outside funding. We take that responsibility very seriously, and we wouldn't have gone forward.
Rockets traditionally use a single engine design for the second stage, but Stoke is pursuing a ring-shaped design with 30 individual thrusters. What's motivating this choice?
Well, it's 30 individual thrusters, but I'd argue that it is actually one single engine. So the power of an engine is, really harnessed in the turbo machinery. So the pumps that take the propellant from the tanks, pump it from low pressure to very high pressure. That's the heart and soul and the power generation of the engine. And we do that one time. We have one single set of pumps that feeds that array of smaller thrusters. So yeah, even though there's 30 of them, kind of the engine is all one thing. What motivates that? Okay, so the engine has to do a lot of things. It has to work at a very high efficiency in space, in the vacuum of space. And that has its own set of circumstances and challenges and environments. But it also has to do some other things. It has to throttle to very low levels of thrust. So it has to operate, let's say, from 10% of its max power all the way up to 100% of its max power. That's difficult traditionally for a rocket engine to do. And it's especially difficult for an engine to do in the high pressure of sea level atmosphere. It's kind of weird to think about, but there's 14.7 pounds for pushing on every square inch of surface in the atmosphere. And that's actually a lot, right? You think about, a 10 inch by 10 inch surface, then that's 147 pounds pushing on that thing. And that's a very different physical environment than in the complete vacuum of space where there's 0 pounds pushing on that thing. So in rocketry, right? So the second stage is typically a single engine. It's relatively big and it's designed to operate in the vacuum of space. And that gives it, a level of efficiency that doesn't work at sea level. And so our distributed system of thrusters is a way that we can make it operate with high efficiency in the vacuum of space, but also perform that low throttle function within the atmosphere.
And it seems like the design is also geared around that single focus on reusability, specifically fast reusability, right? It's solving for the fragile nozzle problem of the traditional bell-shaped extended nozzles, which are more prone to breaking if they were to re-enter the atmosphere, right?
Yeah, traditional bell nozzles for upper stages, they're long, they're pretty big, and they're made out of very, very thin metal, right? And, you can almost think of them being made out of tin foil. It's actually not that different, not much thicker than tin foil, right? So think of that level of fragility.
It's incredibly thin.
It's incredibly thin, right? And so, that's fine when there are no external aerodynamic forces pushing against these things. As an example, actually, if I don't know if you've watched these things, but you can go look up on SpaceX launches, the second stage ignites and you'll see this ring kind of break off as it ignites and comes up to power, breaks off and flies away. That ring is there to stabilize this very thin structure during shipping, during launch, etc. And it's not needed while it's actually burning in space, but it is needed to handle the shipping and the first stage ascent loads. Yeah, so these things are very, 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 very thin. Traditionally, they'll glow red hot, and that's actually the way that they are cooled. But if you were to go and turn around and bring those back into the atmosphere and do so at what starts at 20 times the speed of sound, goes through its own phase of, kind of reverse maximum dynamic pressure, you can just think about the aerodynamic loads that are on this thing. Think about sticking your hand or your arm outside the window of your car on the highway, right? You feel that load. It's not small. And now you think about like a tinfoil structure going out there. And that's a very, 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 very small piece of the effect that we're talking about. that these things have to survive on the way in. And so it's a very different load and design case that you have to plan for.
How are the tests going at the Moses Lake facility in central Washington? I believe toward the end of 2022, you were doing low altitude hop tests of the second stage. You said to Ars Technica at the time, quote, "This is kind of a final proof point of this architecture," end quote. So what's next, and when will testing on the other parts of the rocket begin?
Yeah, so testing at Moses Lake has been going at breakneck pace. It's very exciting to see what we've been able to do in a short period of time. I think that going from our seed stage funding round to the time when we've lit and tested the engine for the first time is right up there with the fastest that it's ever been done, including SpaceX and others. To turn around from basically the fall timeframe and have that ready to fly a vehicle from fall till effectively now is also breakneck pace. We have, I think, all of the really novel elements of this architecture have been proved out on the engine test stand. So that includes this idea of using a single set of pumps to feed 30 distributed thrusters. Operating the engine, what's called the expander cycle, is itself not new, but in this incarnation, there's a lot of newness. And to be able to do that on that time scale is amazing. Our method of steering the vehicle is also new. It's been something that's been talked about in different concept studies for a long time, but it's never really been demonstrated. We have that demonstrated on the test stand. Our integration of the actively cooled heat shield is a major element that's right in the middle, the heart of what's called our engine power balance. So there was a lot of newness and a lot of unknowns about how exactly that would manifest. And we've been able to go through an iterative design and development cycle on that component and get that working integrated with the rest of the system. And so from end to end, the novelty of the system has been proven out on the test stand, which is really cool. The next step is to do a flight demonstration to really prove visually in a visually powerful way that the system works. I think we've got the nuts and bolts. I think, you can assimilate the data and show that this works at this point. The flight test is a demonstration and a proof point that has, obviously a visual, powerful effect. But for a small company like ours, it's also the first time our flight avionics, our guidance, navigation, and control, our communications, our ground systems, our operations, all of those things as a company we're doing for the first time. So that's not necessarily new from a technical or an industry perspective, but it is new for our company. And so the flight test that will happen this year is a proof point for all of those pieces for our company.
If everything were to go perfectly well, which I know is never a matter of course, but if everything were to go perfect, when would Stoke be launching its first rocket all the way into space?
Well, we're looking at 2025.
2025. Okay, that's not too far off.
It is not far off at all.
In the grand scheme of time, that is very close by. Okay, so I've brought up SpaceX a couple times, and it's mostly because there aren't really that many reusable rocket companies to reference for comparison.
There's no others.
The Falcon 9 booster can be used 10 times before it needs heavy refurbishment and up to 100 times before it's retired. I know it's still early days, but with Stoke's ambitious 24-hour turnaround goal and with both stages being reusable, not just the booster, how will Stoke accomplish in 24 hours with two stages what typically takes SpaceX 9 days for one stage? How many times do you picture the full Stoke rocket, both stages, being able to be reused before they have to be retired?
To SpaceX credit, I think their record now is something like 15 uses on a first stage. The 9 days that you reference is first stage refurbishment, but it is not the turnaround time for that system design, right? I think that record is still 21, right? So the 9 days that you're referencing is the time when the first stage is ready for integration, et cetera. But that first stage from one flight to the next flight is actually 21 days.
Considerably longer.
So you have to really think holistically about that whole operations flow. So that's not only refurbishing the first stage, but then it's integrating with the second stage, it's integrating the payload, it's rolling out the pad, et cetera. So that time frame, their record is 21 days, I believe, is still the record. You have to think about every step in that flow from day one and architect not only the vehicle, but the ground systems and the operations element in order to support a 24-hour turnaround. It's a very different problem. Again, you have to be thinking about it from day one. Otherwise, your systems and your infrastructure simply won't support it.
Let's talk about vertical integration. How much of your rocket are you fully building in-house?
Well, we have the capability to build almost everything in the rocket. That includes large-scale propellant tank domes and the tanks themselves, all the way down to very, 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 very precise machining and components like turbo machinery. So we have the ability to make just about everything. And that's important for the R&D environment that we're in, right? So in order to move quickly through research and development, there are things that we'll discover that don't work quite right. We will need to iterate. We embrace that 100, 1000%. It's central to the way we've set up our whole company, right? You know, with the mindset that we have something, we have some level of discovery on a test stand. We know what we need to do to fix it. So the speed at which we can fix it is the thing that dictates the speed that we can develop at. That's where vertical integration is so powerful and so important. We have the ability to make just about everything in a rocket. But that's not to say that we do build everything in a rocket. There are other things that we can plan out when we're making a lot of something. Then we'll look for outside suppliers to do that type of thing. And so, you know, we try to take a strategic and balanced approach to what we build in-house and out of house.
If you don't have that ability to turn around and try a new design and turn around and try a new design, to put it in the immortal words of 2004 era Mark Zuckerberg, move fast and break things, you're not really going to be able to figure out whether or not your designs even have the possibility to work if you have to wait 6 months between every test.
That's right. That's 100% right. I think SpaceX is a great example of that as well. And in fact, I think SpaceX has proven that model. That model was, I would say, not in vogue before SpaceX. And they've proven that, you know, get back to the scrappy design, test, fail, fix cycle as quick as possible is very, very important. That's what they did in the 50s and 60s. That's why JFK was able to say in, 61, announce his mission to the moon. And in 69, we pulled it off. But we drifted away from that mentality for a long time. And I think SpaceX and Elon and Elon's other companies are to credit for us as a hardware industry getting back to that.
To reference JFK, to paraphrase his quote, he said, "We choose to go to the moon not because it is easy, but because it is hard." And one of the things that I think is deeply difficult in general is first principles thinking. But that very thing, trying to understand something, whether it's rocket design or anything else, to go all the way back to the beginning and begin from a first principles approach to be like, okay, why is this built this way? Can it be done a different way? To go all the way back to the beginning of a thing is incredibly difficult. And most industries, most competitors in any industry don't pursue first principles thinking. They instead just say, okay, how is this other person building this thing? And can I make like a little tweak to make it a little bit better so I can get an edge in the market and maybe sell a few more widgets than they are? But to actually like rethink from the ground up a design of something that's been around for decades is really difficult. How do you go about first principles thinking when you're working at Stoke Space, and how are you integrating that approach throughout the company?
In a lot of ways, that's the founding story too, right? I think the key is you start with the problem, right? You hire people who have outstanding fundamentals, can think from first principles. It's not something that everybody can be able to do. You have to have a team that is able to think from first principles and start from the problem and say, given this problem, what's the way that we solve this the best? And that's the story of our second stage. Our second stage starts with the problem. How do you do second stage reusability in a way that has 24-hour turnaround? What does that mean to have 24-hour turnaround? What does it mean to have a vehicle that has a long life, but can still turn around very, very quickly? And what does that mean in terms of the way that we design this thing? And the heat shield is the obvious external example of that, but there's a lot of different elements to the design on the internals that follow that same philosophy. And the key is to be able to think from first principles and design a solution, not because it's been done before, but because it makes sense.
I mentioned geosynchronous orbit and Earth monitoring satellites a little while ago. So let's talk about your company's Earth first approach. On your site, it reads, quote, "Stoke is asking the tough question. How do we grow as a civilization without destroying our home?" End quote. And elsewhere on the site and in interviews, you discuss the company's desire to forward a sustainable future. So let me see how I can put this. A rocket, like any vehicle, any object, is inherently neutral. It can be used for anything. So why is sustainability, right, the Earth first approach, the focus of Stoke's mission? And how do rockets, for our audience, they're traditionally not associated with the concept of sustainability or environmental conservation for a multitude of reasons, right? Whether it's the fuel the stuff that burns up in the ozone. How do rockets help forward your Earth first goal?
We kind of touched on it very early in the interview, which is if we are building this space economy, we better do it in a way that's not only scalable, but also sustainable. So the first part is to look at what we're doing today, how we get to space, and figure out, is it sustainable, scalable? And if it's not, what do we do? What's like the obvious things that we should be doing? And so if you look at the rockets that are launching today, Falcon 9 is burning kerosene. It's very fuel rich. If you look at a picture of a Merlin 1D rocket engine test, you'll see that it's just billowing out this black soot. So, this black carbon is being emitted every single layer of the atmosphere. The alternative to that is also burning kerosene, but it is complemented by what's called solid rocket boosters. So SLS, the glowing white hot exhaust from these solid rocket boosters, is also very damaging to the atmosphere. So anyway, let's go back to black carbon, for example. It's whatever the rocket solution is, it's emitting at every single layer of the atmosphere. And what that means is that the emissions, since it's at every layer of the atmosphere, actually have about a 500 times higher impact on our atmosphere, environment, global warming, forcing functions than surface emissions. So it's particularly sensitive. And the black carbon is pretty damaging, right? It accounts for actually 98% of the radiative forcing impact of a rocket launch. And so I think like the low hanging fruit, the obvious thing that needs to be done is not do that. Let's get rid of the black carbon. And so black carbon is basically soot, right? We don't want to admit that. So that's step one, right? Create the cleanest possible launch solution that we can. And, there's some very simple first steps that we would do to eliminate 98% of the impact. So that is step one. The second part of the question is, why are rockets important for our global existential threat of what our environmental impact looks like? So yeah, we can talk about this for a while too. I think, we talk about scaling our civilization. If you look at the way that our civilization has scaled, it took us tens of thousands of years to get to about 500 million people in global population. But it's taken us only about 200 years, or a very small number of generations, to get from that number all the way up to, we're at 8-9 billion. So it's a factor of about 15 increase in just a small number of generations. So think about that trajectory. How are we going to continue to scale our civilization in a way that's sustainable and doesn't kind of kill our Earth? First of all, we have to look off planet in the long run, no matter what. The other thing that I would say is this impact that we're having is real, but no matter what side of, where you fall on the spectrum, I would argue that none of us really have a comprehensive understanding of the impact that we're having on the environment, however big or small it may be. And so the first way that you solve that is by getting a more comprehensive understanding of the impact you're having. And that means measurements, that means monitoring, that means predicting, that means developing models, and that means putting more sensors and observation equipment into space, right? Space provides you with a global purview that you simply cannot achieve on the ground. On the ground, you can get point source measurements. In space, you can get global and macro measurements in a very meaningful way and quantify it. So you want to be able to do that work regularly on demand. You want your average Joe average PhD student to be able to devise a thesis and instrument and deploy it and iterate on it 2 to 3 times in the course of their dissertation work, right? So typically about 5-ish years. And that's simply not possible. We don't have the access to space in order for a regular student with regular funding to be able to go do that.
What you just said there reminds me of a quote from a former guest of the show, conservationist and wildlife biologist Forrest Galante. He said once in an interview at Google, quote, "Something rare is hard to find and something hard to find is hard to protect." And I think what you said is very relevant there. If we don't have the data to understand what's happening to our planet, then we won't even be aware that we need to do something to fix it. It seems like that's why satellites, and even more satellites than we have currently, is why it's so important in regards to the environment.
That's right. There's immediate impact that satellites can have on our well-being, right? So for example, we don't have a good measurement of how much fresh water we have on Earth. We don't know what the freshwater supply is. Maybe it's good, maybe it's bad. So let's measure that. We are beginning to, but don't yet have a great way to track agricultural disease, right? Especially across borders, especially in underdeveloped countries where a lot of the agriculture is done at the village or town or city or even state level. We don't have a good way to predict fresh water supply, especially in these underdeveloped countries that then lead to famine. And satellites provide you with that data. It allows us to do that predictive modeling and get ahead of some of these and make sure that the infrastructure and the aid is in place to help these people.
I want to circle back to something you said about the black soot being injected into the stratosphere with traditional rocket fuels. I want to read something for our audience to kind of help ground them in the dire need for us to move beyond those fuel sources. There was an environmental impact study that was done by researchers from the U.S. National Oceanic and Atmospheric Administration, which found that, quote, a tenfold increase, that means if there's 10 times more launches in the future than there are today, which seems eminently reasonable, a tenfold increase in the amount of soot injected into the stratosphere every year would, after 50 years, lead to an annual temperature increase in that layer of 1 to 4 degrees Fahrenheit. The study found that the projected warming would slow down subtropical jet streams, bands of strong winds circling the planet at the lower edge of the stratosphere that influence African and Indian summer monsoons. Warmer temperatures in the stratosphere would also degrade the protective ozone layer, which blocks harmful ultraviolet radiation from the sun from reaching the planet's surface, end quote. So the need to transition to the kind of fuels that Stoke Space is going to be using is very necessary. On that same note, Andy, with a tenfold increase of rocket launches causing that dire of a consequence, right? I started to wonder, okay, with a 24-hour rocket turnaround time, and our ability to send more and more rockets into space to launch more and more satellites, right? Which forwards a goal that I think is very important, like we're talking about. We need to be able to monitor these parts of the world, whether it's for climate change or all the other reasons that you mentioned. But I came across something during my research known as Kessler syndrome or collisional cascading. I was wondering if you could kind of loop our audience in as to what that is. And are you afraid of us ever getting to a point where there are so many satellites in space that that could possibly happen?
Well, two very different effects that you're talking about, right? Well, the first one is effectively emissions. And I think that boils down to if you're a child or a person of, let's say, the 1980s and beforehand, you're familiar with wheelers just billowing out this black soot, right? From an environmental perspective, it's pretty obvious that it's a go-do to get those vehicles off the road, right? So that's the way I think about kerosene rockets, just like an obvious go-do.
Absolutely.
And then the Kessler effect, we have a number of objects that are orbiting Earth. In order to orbit Earth in low Earth orbit, you go about 17,000 miles an hour. It's really fast. And so if two of those objects are to collide, then it's not too surprising that you have this kind of explosion and debris field that results. So now you have hundreds or thousands of more particles and objects in space. And since you have more objects in space, now it's not too hard to understand that those things have a higher probability of colliding with other things. And so the Kessler effect is you can get to a point where this is a cascading and snowballing effect where you wind up with effectively a cloud of all these objects that you kind of can't get through. That's obviously a eventuality that we want to and need to avoid. Like I said, we're like before the first inning in the ball game of space evolution here. So it's very early and it's something that we have to think very seriously about. And so there's a whole layer of the space economy that is focused on situational awareness. We need a national and international system of agreements that set standards for what we deploy into orbit, how we behave in orbit, what we do and don't do in orbit. And then we need a way to enforce those standards. And those things aren't quite in place yet, which is very, very important. The U.S., National Security and Department of Defense take this very seriously. This is why in the last couple of years, there was the formation of the U.S. Space Force. And there's a lot of things happening in space that require not only international cooperation, but an international system of rules, and then the ability to enforce those rules, which is the charter mission of our, national security space and the Space Force. So it's very, very important.
Yeah, understandably so. Avoiding collisional cascading is a problem bigger than just one company like Stoke Space can solve. But as I began thinking about, okay, well, if you achieve that 24-hour turnaround time, if more companies follow suit, if we're launching objects into space, satellites or otherwise, more and more frequently, I started to become afraid of something I didn't even know I had to be afraid of until I began researching this topic.
Yeah. Well, look, it starts with situational awareness, like I said, right? Like, do all the players know where all the things in space are? Today, the answer is kind of no. And then the next question is, who dictates the traffic, right? What's flight traffic control? What's the FAA equivalent for space? And right now, you have to be certified by FAA to get out of the atmosphere, FCC for where you're going and what your plans are. But I would say that once you're in space, it's kind of the Wild West still. And so that's the next evolution. That's important, but we don't have the commercial infrastructure to be able to respond to that yet. That's why space is so exciting. There's a lot of stuff being built, and that's one of them. The ability to A, provide that situational awareness, and then B, kind of regulate and dictate how things move around space in a way that is responsible. So all of that is in work on both the regulatory side and the technical side.
What are some things over the last 3 some odd years that the Stoke team has learned so far, both from its successes and failures?
Well, I think a lot of the learning has been validating. We started out, we had this idea. It's a new and different idea. Some of it is drawn from a lot of things that have been proposed but never tested in history. And we're kind of the first ones that are out there testing these things. I would say from a management and company building perspective, there's a lot of things that we thought were important. But again, are we able to execute on them the right way? I don't know. And so a lot of those things have, I would say been validating in the way that we've set up our company and started to run our company.
What is something or some things that can go wrong in the next stages of production and testing, and how is the company preparing for them?
Well, a lot can go wrong in our business. When they do go wrong, typically they go wrong spectacularly. And if you think about what a rocket is, it's a controlled explosion. And if it ever becomes uncontrolled, then that's a spectacular failure. So that's just the nature of the business that we're in. And the way that you prepare for that is, first of all, in your facilities and your systems, you build them in a way that is as tolerant as possible to those failures. And then the second thing is you set up the company to be ready to respond and recover from those failures as fast as possible. The vertical integration element that we talked about is kind of a number one central and important to that. If you have a failure and you're reliant on third-party suppliers to help you recover, then you're going to be in a world of hurt. But if you can control your dependencies, push where you need to push and, kind of work that way, then you can recover much more efficiently.
2 more questions to wrap us up. If you could paint a picture for us, describe the future of rocket launches once Stoke is fully operational. What will be radically different from today? What might people be surprised by? What can they look forward to?
Well, it's amazing, right? Like I said, we're warming up for the early innings, right? In the industry. So the mode of transportation is a whole new mode of transportation. It's like the invention of ocean-faring sea vessels, right? The steel-hulled ships with steam power compared to wind sail ships. It's an invention of aircraft. It's an invention of rail, right? It's a whole new mode of mobility. So if you are looking to get something into space, you can book that ticket the same way that you book an airline trip right now. You can book it a year in advance if you want, or you can book it 2 days in advance. You can get a seat on that vehicle, which is going where you want, when you want. It's very different from the world today. So that's number one. Number two, it's a whole new mode of mobility. One of the things that the reusable second stage unlocks is this ability not only to go to space, but then to come back from space. And you may want to land at the original launch site so you can turn around and launch again. But maybe you actually don't want to go all the way to space. Maybe you want to land on the other side of the world. And you can do that in under an hour, right? So do half an orbit instead of a full orbit, right? So you launch from one place and you land anywhere in the world in under an hour. The first place where that's very interesting is probably with ferry or aid applications. But eventually, when the cost comes down and our ability to do this in a very repeatably, highly reliable, and regular way, there's a whole lot of commercial applications that then begin to make sense. So I would just say that it's an entirely new mode of transportation, which is starting to take hold and is very important. It completely changes the way that we move goods and services, not only around the world, but also into space.
Yeah, the idea of being able to hop over to the other end of the world in an hour is mind-blowing. The possibilities seem endless. Okay, so last question, Andy. What's something that the layperson may not appreciate about what your team is accomplishing right now? What's something that's really exciting you about Stoke's work that you'd love to share with us?
I think there's a lot of things. The scope of what we've been able to accomplish in a very short amount of time, to me, has exceeded my expectations. The way that we've done it. I'm very proud of that. We've done it in a way where we have hired just incredible talent, and it's a management philosophy, tried to put people in a position to succeed, remove all possible barriers from them in order for them to succeed and do it and execute. I'm really proud of the culture that we're building. To your earlier questions about, can you do this, but also maintain relationships with friends and family? I think the answer so far is yes. We've created different forms of flexibility in order to make a child and family friendly environment. Yeah, I guess I'm just really proud of what we've been able to do, but it is still really, really very early. And so the big question is, are we going to be able to scale it? And so far, I think the answer is yes.
Andy, one of the reasons I love talking about technology is, to me, it's a kind of time travel. It's a way we can glimpse into the future to see what's coming. And learning about Stoke Space's mission, its goals, it makes me so incredibly excited about what's to come. I think you and your team are taking really big swings and accomplishing some pretty fantastic things. It's been a real pleasure researching your company, learning more about what it's accomplishing, learning more about its mission. And it's been so great talking with you today. So thank you for your time. And honestly, thank you so much for what Stoke is accomplishing.
Well, thank you so much. Appreciate the kind words. Appreciate you having me on. And it's been a pleasure.